Okay, I'm Jeroen, and this is a question from an exam from 2012, I think, about astrophysics and exoplanets. So the question is about the TRAPPIST, which is a robotic telescope that is designed to detect exoplanets, which are planets outside of the solar system. So there is light coming into this telescope, and then the signal is being detected on some sort of detector over here. And the detector has a quantum efficiency of 96%. And then the first question on this exam is, what does it mean to have a quantum efficiency of 96%? And it means that when light comes in and when a photon hits this detector, there is a 0.96 chance that that photon will actually be detected by the detector. So this particular detector will only detect 96% of all the light that will be coming into this detector. So that's the first question. And the second question is, when you have this particular telescope, when light is coming in, it will be sort of focused into a point onto this detector here, something like this. But if there is light coming in from a signal, from a star, for example, over here, but if there is other light coming in from the star that's very nearby, it might form some sort of blob on the detector that is very close to it. It might be very hard to dissolve these two different points, because they might look like two overlapping blobs. And now there is an equation that you have to know that tells you how big this blob is going to be for a certain wavelength and a certain size of the lens that you're using. So in this case, and this is what question 2 is going to be about. So in this case, the size of the mirror that the telescope is using is 0.6 meters. And the wavelength that we're observing with this telescope and that this detector is sensitive to is, I think, 715 nanometers. And then the question is, what is the angle that this telescope can still resolve two different signals from? So if there is a star over there and there's a star over there, there's a certain angle between those two stars. So let me draw that over here. Then what is the angle that this telescope can resolve them and see that you get two distinct blobs on your detector? Now, what you need to know is that this angle is determined by the size of the mirror or the size of the lens that you're using, and it's inversely proportional to the size of the wavelength. The equation for that is that this angle is going to be lambda over the diameter of this mirror or of this lens of your telescope. So it's going to be 750, and these are nanometers, so this has to be times 10 to the minus 9. And then you divide it by 0.6. And then you see that the angle in radians is given by 1.25 times 10 to the minus 9 radians. And then the third question is, now imagine that you're looking at an exoplanet, so a planet around a star that is 10.5 light years away. And there is a planet circling around that star. And this planet is circling around this star in an elliptical orbit. And at its closest point, it is 1 astronomical unit removed from the star. An astronomical unit is the distance that the Earth, on average, is removed from the Sun. And at its furthest point, it is 5 astronomical units removed from the Sun. Then, will you be able to actually resolve the star and the planet individually using this telescope? So, in order to calculate that, you want to know what the angle is that you're going to see from Earth between this star and that planet, and then hope that that angle is going to be it's going to be more than the angle that sort of gives you the minimal angular resolution of your telescope. So to calculate that angle, you can see that you have to take the tangent, the tangent of that angle is going to be proportional to this 5 astronomical units divided by these 10.5 light years. But because this is a very small angle, you know that the tangent of this angle is roughly proportional to the angle. So the only thing that you now need to do to calculate this is insert these numbers in here, 5 astronomical units in meters. It's going to be 5 times 1.5 times 10 to the 11th meters. And 10.5 light years is going to be 10.5 times 9.45 times 10 to the 15th meters. Put these meters in there. And then if you put this in on your calculator, you will see that this is 0.0755 times 10 to the 11th over 10 to the 15th. So it's going to be 0.0755 times 10 to the minus 4. Or if you want to nicely rewrite it, it's going to be 7.51 times 10 to the minus 6. So you see that that angle that you have over there is indeed a lot bigger than the minimal angle, the angular resolution that your telescope can distinguish two things from. So you would naively think that you can indeed observe this, if there is a planet that is so far away from a star, and it is 10.5 light years removed, then you would guess that indeed this would work out, right? However, in practice, so this is brings us to the fourth question. Explain why it is unlikely that a telescope could be used to observe this planet directly. But there are various reasons why this might, in practice, not really work out as nicely as on this whiteboard. One of the reasons is that when this telescope is located on Earth, it looks through the atmosphere, and the atmosphere will sort of disturb the signal coming from that star, and there will be a lot of noise that might make it very hard to actually distinguish this star from the sun. Another thing is that the sun here, or the star, is so much brighter than this planet that it's going to be very hard to distinguish on your detector this very bright spot that is millions of times brighter than this very tiny planet that is going to be located next to it. So that brings us to the end of question through 2b. So yeah, that is how you would calculate something like this.